All right, so what is chemistry? What is chemistry? Yeah.
Chemicals?
Can't use the word in the definition. Yeah.
The study of how substances react with each other and how they're composed.
That's a pretty good definition. That's not bad at all. All right, we're going to define chemistry as the study of matter and how it changes. That's actually really, really close in line. The study of matter and how it changes. How many of you have studied chemistry at some level before? Like you saw the periodic table in 7th or 8th grade? About half of you, all right? This is always the standard answer that there'll be like 10 hands go up and then there'll be like 4 people that are like halfway up. Like, I don't know, my teacher said there was a periodic table. The study of matter and how it changes. So to be able to use that definition, we have to be able to define matter, right? Matter is defined as anything that has mass and takes up space. Anything that has mass and takes up space. We redefine chemistry then as the study of anything that has mass and takes up space and how it changes, right? So let me ask you this. Is Will's pencil matter?
Yes.
Is Will matter?
Yes.
Does he matter?
Yes.
Sure. Will is matter, his pencil is matter. Is the air that he's breathing matter?
No.
Yes.
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 It does.
Does it take up space?
No.
Yeah.
Yes.
How can, so David, how can you prove that it takes up space? Yeah.
Fill up a balloon.
Fill up a balloon. Does take up space or just breathe? Look, air takes up space. All right, simple enough. Air takes up space. Does it have mass?
Yes.
Yes, it does. All right. Now, it is harder to observe that, the mass of air, because it's very low density, and so it's floating around. So we can't just, I'm going to put some air on the scale. All right, it's not how it works. But we can contain it and put it on a scale. All right, or put it in an environment where it's more dense than other substances. But it does have mass and it does take up space. So air is matter. Yes.
So if like air had more density than it did, it would just be like float on the ground, we have to like go down there and breathe.
If you consider, yes, like on very high altitudes, right? So consider, like if you have dry ice, for instance, dry ice sublimates, and so it turns directly into CO2 gas, which will smother you. All right, so you can't just put some dry ice in your back seat and drive somewhere, and then it melts and turns into gas, and you breathe it in, and you're like, you die. Because it's more dense than air, even though you can't see it. If you looked at it, you're like, oh, look, more air. Because it's colorless, right? It's colorless gas. And so you breathe it in, and it's more dense, and so it sinks in your lungs, and the air can't get in. You suffocate. All right? So, so, I mean, air is more dense than other things. All right? And we're going to look at that composition and density later. But air is matter. All right? Is light matter?
Yes.
Yes.
Yeah.
No.
If this is a no.
Can you weigh light?
Can you weigh light? All right, so this is a really difficult question. So years ago, we would have answered this question with a definitive no. We would have said no, light does not matter because it does not have mass and take up space. It's a wave of energy. All right, it's electromagnetic wave. It's radiation. Light is radiation. So we would have said no, but as we study it more and we get into quantum physics, we understand more and more that we're talking about high energy particles, which do have a very, 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 very small mass, photon packets of energy. So that is beyond what we're going to study. All right. So for the concepts in this class, we'll say light does not matter. However, I want you to understand there are parts of physical science where it's definitely considered matter, but we're not going there. All right?
Light is not matter.
So.
Correct.
So
There you go. Thank you.
So it is matter, but we're just going to say it's not?
Because it's such a finite amount that it's not relevant to us. All right? So I will show you a video at some point, probably a couple weeks, of this video. It's actually called What the Bleep video. I don't know why they named it that. It sounds bad. But it's like a cartoon talking about an introduction to quantum physics and high energy radiation. So we'll get into that. It's called the double slit experiment. So we'll look at that video just to kind of give you an idea of how all that happens. All right, but as far as we're concerned, light is not matter. But that's one of the places where when we broke down the three main branches of science, and we said that physical was one that included physics and chemistry because there's so much overlap between the two. When we get to that level, that's where there's so much overlap. All right, is in waves and what the actual particles are doing, interacting together. Now, so chemistry is the study of matter and how it changes. So basically, anything that has mass that takes up space, how that changes. All right. Now there are two laws we need to go into before we go any further. You're probably familiar with them, or at least heard them mentioned: the law of conservation of matter and the law of conservation of energy. The law of conservation of matter says matter cannot be created or destroyed. Law of conservation of matter. Matter cannot be created or destroyed. And basically, what that says is the total amount of stuff in the universe is always that amount of stuff in the universe. All right? So however much stuff is here now is the amount of stuff that's always been here. Now, we can get back to that original question, where all this stuff come from. We're not going to answer that today. It's a little more difficult than today. All right? But basically, the amount of stuff has always been the same and always will be the same. Yes?
How is that true? Because we have more humans now than we did 100 years ago.
We're also consuming air. The amount of stuff doesn't change. If I eat this paper, I have more mass, but there's no mass of the paper now. The amount of stuff is still the same. Make sense? So matter can change forms. Matter doesn't vanish. And it doesn't just randomly show up. All right. So the second one is law of conservation of energy, which is worded the same. Energy cannot be created or destroyed. All right, so what we need to understand is the total amount of energy in the universe is consistent. Energy doesn't just appear, it doesn't just vanish. All right, if I throw a ball to someone, and we'll get more into this physics because we're doing physics in January now. But if I throw just Croman's in the back, if I throw a ball to Croman, I'm releasing energy, and when he catches it, seems like the energy stops and goes away, but it goes into energy into his hand, which is transferred into thermal energy to make it hotter in his hand. It dissipates, it seems minimal, but it's there. And so energy never just vanishes, it turns into other forms of energy. All right? Energy comes from somewhere and goes to somewhere, but there's always the same amount of energy everywhere. All right? The total amount of energy in the universe is consistent. You go back to the same question we asked before, where does the energy come from? We're not getting into that question today, or probably ever in this class, but where did all the energy come from? Where did all the matter come from? Great questions of life. All right, so continuing on. So all matter is made up of tiny particles we call atoms. All right, and atoms, first thought of by a guy named Democritus. Democritus came up with the first idea of the atom. The word atom in and of itself means it can't be split, which is actually wrong. But we didn't know that at the time, so we called it an atom. And basically, Democritus said, I cannot prove, but I think that all matter is made up of little tiny particles. All right? And it was some 400 years later before Dalton came through, and Dalton came up with Dalton's atomic theory. It says all matter is made up of tiny particles called atoms. And he said they cannot be subdivided, which is wrong, but he made great advancements for us anyway. So Dalton's atomic theory, not quite right. He said they couldn't be divided, they can be. But he made great strides in kind of proving what Democritus had said years before. All right? And then as we come forward, we'll get into more in the next few days. We'll get into atomic structure. All right, we're going to do a little bit today. But Niels Bohr, and then further into the modern atomic theory and what the atom actually looks like. But Democritus, followed by Dalton, came up with the original ideas of the atom. Now, atoms, again, are defined as the smallest particle of an element that still retains the properties of that element. The smallest particle of an element that still retains the properties of that element. You good? You good? Did you draw that? Nice. You can draw stick figures. Smallest particle of an element that still retains the properties of that element. And so while we can break an atom down further into subatomic particles, which we'll do momentarily, and into quarks, and we can break them down further, the smallest we can divide it, it still represents that element really, is to the atom. All right? The atom is made up of 3 subatomic particles. Most of you have heard of these before. Subatomic particles. And there are 3. And I am going to be intentional about color coding these, just so you're aware. All right, so the first ones are protons. Protons have a what charge? Anybody know? Positive. Protons are positive. That's easy to remember because the prefix pro means positive. So positive charge, and these are found in the nucleus of the atom. The second subatomic particle is the neutron. And neutrons have a neutral charge. Now, a lot of people will say negative because they see that Ne, but it's neutral, neutron neutral, right? A 0 charge, and those were also found in the nucleus. And what's the last one? The electron. Electron, and electrons have a, if you have trouble, it's easy to remember pro, it's positive, neutral. But if for some reason you get confused, getting electrocuted is a negative thing. Easy enough. All right? Most often. All right? And these are found in the electron cloud. Now you'll find that for the rest of eternity, I will probably write E minus for electrons. So anytime you see me just write a little E or minus, or E minus, that's electron. So they are in the electron cloud. Now, if you forget when you see the term subatomic, sub means what? Below. Sub means below. All right, so like a subway is below the roadway, right? Sub-zero is below 0 temperatures. So subatomic is below the atom, smaller than the atom. All right? So these are things that make up an atom. So in an atom, all right, in the middle we have protons and neutrons. So what I want you to do is go ahead and get out your periodic table, yours or the one in the book, I don't care, either one's fine. And we're going to look at a very simple example. We're only going to do one example today. We're going to get into gross detail and atomic structure here in the next few days. But we're going to look at a very simple example. All right? So we're going to look at the example of helium. For now, we're going to assume that whatever the atomic number is, that it is the number of protons, neutrons, and electrons. Now, that's not true. All right, we're going to assume that for now. It is the number of protons always. Number of neutrons, starting out it is, but not down the road. Electrons, those change a lot. Yes?
You talking about isotopes?
Yes. So, when we talk about number of neutrons, yes. So, and we will get into isotopes this year for sure. So protons for sure, but neutrons and electrons, those vary. But we'll look at the atomic number for helium. What's helium's atomic number? 2. The atomic number is 2. All right? Atomic number 2. So you're going to memorize all those, right? Those 40, right? So atomic number is 2. So we're going to assume for now that it has 2 protons, 2 neutrons, and 2 electrons. So in the center of the atom, we have the nucleus. And it is made up of 2 protons and 2 neutrons. Nucleus. Made up of 2 protons and 2 neutrons. And those are held together by something called strong nuclear force. All right? And then on the outside, in the electron cloud, we have 2 electrons. And what you find is the mass of the electrons is significantly smaller than that of the protons and neutrons. We're going to draw them the same size for simplicity's sake at this point. Now, what is the overall charge here in the middle? What is the charge of these 2 protons?
Positive.
2 plus, right? We have two protons, so 2 plus. And what's the charge of these 2 neutrons? 0. So what's the overall charge in the middle?
2 plus.
2 plus. And what's the overall charge here on the outside? We have 2 electrons, which is 2 minus. And so if I have the whole atom has 2 plus and 2 minus, the overall charge is 0. All right, net charge of 0 on this atom. All right, so we have a helium atom here with 2 electrons, 2 protons, 2 neutrons. The overall charge of the nucleus is 2 plus. Overall charge of the electron cloud is 2 minus. So a total charge of 0 for this atom. All right. Now what we're going to spend a lot of time, and you guys are going to get really good at drawing circles, is we're going to look at Bohr models. Bohr is a Danish physicist. We're going to look at Bohr models of electron clouds. And so basically, we're going to draw lots of circles around this and find out where all the electrons go and their energy levels. All right, which is one of my favorite things to do. Some students love it because they think it's a lot of fun, and some students cry a lot. All right, so we're going to spend the next week or so. All right, so what we're going to do is we're going to stop there. I'm going to give you the last half hour to finish your flashcards, coloring your periodic table. If you get done with your flashcards, go ahead and start studying them. All right?